Problem A2. Consider two objects with equal heat capacitance C and the initial temperatures T1 and T2. A Carnot engine is run using these objects as its hot and cold reservoirs until they are at equal temperatures. Assume that the temperature changes of both the hot and cold reservoirs is very small compared to the temperature during any one cycle of the Carnot engine. Question A. Find the final temperature Tf of the two objects and the total work W done by the engine. Now consider three objects with equal and constant heat capacity at the initial temperatures 100 Kelvin, T2 equal 300 Kelvin, and T3 equal 300 Kelvin. Suppose we wish to raise the temperature of the third object. To do this, we could run a Carnot engine between the first and the second objects, extracting work W. This work can then be dissipated as heat to raise the temperature of the third object. Even better, it can be stored and used to run a Carnot engine between the first and the third object in reverse, which pumps heat into the third object. Assume that all work produced by running engines can be stored and used without dissipation. Question B. Find the minimum temperature TL to which the first object can be lowered. Question C. Find the maximum temperature TH to which the third object can be raised. Solution for problem. Question A. During Carnot cycle we have four processes. Two processes are adiabatic, during which delta Q is 0, and two isothermal processes when we have this equation. Because this Carnot cycle is a closed cycle and reversible, we have a total change of entropy is 0. And this change of entropy it's only during isothermal process. So we have ds1 plus ds2 equal this expression, and this equal 0. And now, because heat capacitance is the same for both objects with the temperature T1 and T2, we have dq1 equal c dt1 and the dq2 equal c dt2. Now we can put them in this equation and find that during one cycle we have this equation where delta T1 and delta T2 is very small, and we can integrate whole process. After integration we have this equation. It means that T final over T1 equal T2 over T final, and finally we have Tf equal square root from T1 multiplied by T2. Let's count what is work W done by the engine. Total change of internal energy of these two objects with initial temperatures T1 and T2 equal this expression. It means that due to the first thermodynamical law, we have work done by all these processes equal due to change of internal energy, which is this expression. And that will be answer for question A. Question B. Find the minimum temperature TL to which the first object can be lowered. Solution. Due to the second thermodynamical law, we have minimum TL could be equal T1, which is 100 kelvins, because during this process we cannot get temperature less than minimum temperature of this object. In other case, we could run process to run heat from lower temperature body to higher temperature body. And this is the answer for question B. Question C. Find the maximum temperature TH to which the third object can be raised. Because total change of entropy for whole three objects must be 0, we have a final expression that T1 multiplied by T2 multiplied by T3 must be constant during this process. Also, due to energy conservation, we have sum of temperatures must be constant. When we assume that third object has highest temperature TH, two other must have the lowest temperature T0. It means that we have these two equations, and using these initial numbers 100, now eliminating T0, we have this equation, and one root of this equation, it's obvious, that's TH equal 100. It means that rest we can convert to quadratic equation, and we have finally this expression, from which we have other two roots, 400 and 900. But because of energy conservation, 900 is not possible, so it means that the real answer is 400. It means that the final answer is for highest temperature is 400. That was a solution for question C.